Good day, everyone. Thank you for spending time with us on this webinar to discuss ways we are addressing carbon reduction for our customers. My name is Chris Lyons, your host and moderator for today. I've been working in the energy industry for the past 40 years, with more than half of that time at Solar Turbines. But as you can imagine, I've seen several cycles, changes, and impacts to our business over that time. I started my career in 1979 working predominantly in the Gulf of Mexico, where we experienced the second oil crisis due to the decreased production as a result of the Iranian Revolution. If any of you remember, if you go back that far, the long lines you had to wait just to get gas. But at that time, oil prices doubled in less than 12 months to $40 a barrel, 40 years ago. Today, we're below $20 a barrel after a speculative peak of $184 per barrel in June of 2008. So it'll be interesting to see the next wave of changes and how the energy industry will transition going forward. As an essential business and one that has its factory still in operation to serve our customers, we are concerned with this pandemic and the safety of our employees, suppliers, customers, and all our families and friends. We hope you have the ability to work in a safe environment, and we hope soon we'll be back to a normal mode of operation. I'm not sure what that'll be, but hopefully soon. All our offices staff are working from home, and those presenting today are working from home. So please bear with us if we run into any technical difficulties as we move through this process. We feel we put together some excellent segments geared toward our oil and gas customers, addressing the topics of energy efficiency and optimization, carbon capture, storage and utilization, methane emission reduction, and lower carbon fuel options. So that'll take us about 15 minutes for each of those topics, and then we have a question and answer period at the end. But during this time, if you'll notice in the right side of your screen, you should see a chat box where we'd appreciate if you could put in your questions, and we'll try to address them at the end of the presentation segment. We're also going to do a live polling where we'll get some feedback from you, and you'll be able to see others' opinions on the whole issue of carbon reduction. So for some webinar information, we will have a recording of this. The slides will be available as well, so you don't have to take all the notes. As mentioned, we would appreciate you putting in your questions into the question box so that at the end we can try to specifically address them. Any issues that you may have, you can contact Kim Cruz during this. She's online with us as well. So why a webinar on carbon reduction? Over the past year, we've had considerable interest on this topic. Despite the current and hopefully temporary downturn in the use of oil, we still feel it is an area that will have to be addressed to remain a vital industry over the long term. As you can see from this slide in the diagram on the left, our atmospheric concentration of CO2 is at its highest level in recorded history at just around 450 parts per million. With, if you look at the increasing that over the last 20 years, it's been pretty significant. The middle chart shows the continual rise in ambient temperatures, with the average global temperature increasing just a little over 1 degree C or 1.9 Fahrenheit, higher than since the last 19th century, with the warmest 19 of over the last 20 years, 19 of those have been the warmest on recorded history. So on the right, for people like us who live in San Diego in a coastal environment, we're also seeing sea level rises. And over the last 10 years or so, we've seen a just over maybe 80 millimeters, 3.3 inches. But over the last few years, that acceleration has continued to grow. So a lot of statistics that say we have to be concerned about carbon in the atmosphere. If you also look at this slide, you see the projection. If we continue at the pace we're at now, that the CO2 will continue to increase. And if we don't do anything, the global temperatures will continue to rise, where then it could result in some catastrophes, as we're already starting to see, fires and floods and all kinds of things. So the international or the Intercontinental Panel on Climate Change suggests that we keep it to a temperature rise of 1.5 C, no more than 2 degrees C. So you see that in the future, if we continue to move at the pace we are, we're going to have to deploy ways to reduce our carbon footprint. So on that basis, we'd like to get into our topics. The first one being energy efficiency and optimization. And for this, we have a great speaker on this, Christopher Banchero, who will address this topic. Christopher is a U.S. Naval Academy graduate and served as a lieutenant as a nuclear marine submarine officer. Christopher has been with Solar for the last 15 years and is our digital business development manager in our service group. So Christopher, the floor is yours, please.
Thanks, Chris. I appreciate the introduction and the opportunity to speak with all the folks joining us on the webinar. As Chris mentioned, I'm the digital business development manager for Solar Digital. Now, I'm sure most folks, hopefully on the webinar today, know Solar Turbines as a manufacturer of industrial gas turbines and centrifugal gas compressors. Some examples of our product line are shown here in the slide on the left. Applications such as gas compressors, generator sets, and even electric motor driven compressors in the very bottom there. The group that I represent is Solar Digital, which supports our customers, what we call customer services, or basically our aftermarket division. Solar Digital works on our proprietary system that we call Insight Platform, which supports our customers with remote digital technology and digital solutions to really make sure that our customers maintain the highest availability and reliability possible. With remote technologies such as the Insight Platform, our fleet managers can help our customers proactively manage their turbomachinery fleets all around the world, from the comfort of their homes due to this COVID-19 crisis we're dealing with at the moment. One of the topics that I wanted to discuss today is specifically power optimization, and basically how we can help our customers better dynamically balance their energy supply and demand needs so that they can actually execute lean energy management without having to compromise the stability and reliability of the facility power at their facilities. And what this allows our customers to do is actually actively participate in their carbon footprint reduction. If we look at a typical offshore installation, we're looking here at an offshore platform. If we delve in deeper, we can see a lot of the major assemblies that are typically found on an offshore oil rig. You see on the left-hand side things like the heli deck and the living quarters. Down on the mezzanine deck, you would typically have things like your power generation modules. On the right-hand side, you can see the flare boom, the production modules up on the weather deck, gas coolers, as well as the pedestal crane. So this is typical arrangements that we would see at most of our customers' facilities. Now, of all these, the two that are probably most germane to solar turbines and our machinery is that our equipment is typically used in power generation applications as well as the production modules on most of our customers' installations. In this example here, I have 6 Taurus 60 generator sets providing electrical power for the facility. And on the production side, we have a bunch of Titan and Centaur compressor sets, which would represent kind of the higher, second to largest and second to smallest of our product line, whereas the Taurus 60 is pretty much right in the middle of our product portfolio in terms of size range. Now, since we're talking specifically about power optimization, I'm just going to focus on the power generation equipment. So for each of these Taurus 60s, we have a gas turbine that's basically converting all of the fuel, which is typically going to be natural gas or diesel, into energy that allows the rotation of the generator shaft through a reduction gearbox. And so that's what's going to generate all the electrical power. Now, a Taurus 60, if we look at our typical, this is our 7801 engine rating. And I've done some calculations here to look at different T1 temperature ranges. So the ambient temperature range, everything from 4 to 43 degrees C. We would typically expect the output power to be anywhere between 4.1 to 5.5 megawatts. So this would just be our standard combustion application for a Taurus 60. So for all intents and purposes, I'll refer to each of these Taurus 60s as capable between 4 and 5.5 megawatts. Now, what we see for a lot of our customers, they're enrolled in a program that we call Equipment Health Management, which has a solar fleet manager, and the units are connected to Insight Platform to allow us to have all of our remote technology and analytics to see the operation of the machine. Now, what we typically see in offshore installations is our customers will typically load up and run each one of the power generation units and equally distribute the load. So what I have here is a year's worth of data looking at the load profile. And this particular customer's application is very similar to those that we see all around the world, that we have 6 engines, all lightly loaded and sharing the electrical power needs for the entire installation. When we actually look at the historical data, you'll see that units A through F, at their max, in the last year of operation, we never saw anything above 4.55 megawatts. Whereas the average historical output was closer to about 3.3 or 3.4 megawatts. So when we compare that to the 4 to 5.5, that's 100% capacity of these engines, they're well below what they're capable of. And the operational philosophy is pretty well understood that for most of our offshore installation managers responsible for the operation of the platform, their primary priority is to protect the platform production. In which case they'll typically run all the generation equipment with rather low loads with a very high spinning reserve, meaning that they have the capability of producing much more power than they currently are. So as we talk about carbon reduction strategies, I believe now with a lot of the technology we have available, we can allow our customers to continue to protect their platform production, but perhaps do it with less power generation equipment. If we look at this example again, so we have 6 units in operation, and I looked at the historical platform load was around 16 megawatts. So for the purpose of this exercise, I went even more conservative and basically base loaded at 18 megawatts at 80 degrees Fahrenheit or 26 degrees Celsius. So in this application, all 6 units are running at about 62% of their rated capacity. So they're basically each generating 3 megawatts of power. So what this means is that since all of these units are capable of 4.8, so each unit's capable of going 1.8 megawatts higher, we have a 10.8 megawatt spinning reserve available in this application. Now, I think most could quickly identify that if we were to reduce down to 5 units, even then we would still be operating with 5 units, each at 75% capacity, generating 3.6 megawatts. Even with 5 units in operation, we can see that the customer still has 6 megawatts of spinning reserve capacity should the platform load have any sudden increases. And in fact, if given the size of the engines and the capability of them in this instance, we can actually reduce it all the way down to 4 units in operation. So each of the engines operating at 94% of their capacity, generating 4.5 megawatts apiece. Even in this scenario, we still have a 1.2 megawatt spinning reserve available to maintain reliable power on this platform. Now, if we were to say, look at a load increase on this particular platform from 18 megawatts up to 21 megawatts, again, the ambient temperature being the same at 80 degrees Fahrenheit or 26 degrees Celsius. Now, in this instance, we would notice that if we had a platform load increase to 21 megawatts, even if the engines also went up to their max rated capacity of 4.8 megawatts, we would have a 1.8 megawatt spinning reserve deficit. And if in the absence of any mitigations, what would happen is essentially these 4 running machines would attempt to assume the load and try to continue to produce power. But inevitably, they would not be able to reach the demand, and then they would start tripping offline and the platform would go dark. So for power optimization, we have a few different options to explore. So option 1, so customers that have equipment health management would be able to activate what we call power boost. In this instance, we can get upwards of 10% additional power out of an operational engine. So in this case here, we could run these engines up to 109% of the rated capacity, and they would be able to generate 5.25 megawatts apiece. In which case, we'd be able to meet the 25 megawatt load, and we would have basically deplete any spinning reserve capacity. Now, this would buy the operations some time to start up units E or F to reestablish a healthier spinning reserve capacity. But this would prevent the entire platform from going dark. So option 1 would be the activation of power boost. Option 2, if the customer had elected to install any battery energy storage system, these units are capable of generating upwards, I believe, of 4 megawatts given the size. This would allow basically another avenue so that we could be able to start discharging from the battery energy storage system to make sure that the to regain a healthy spinning reserve. The third option we could explore is the use of a power management system to shed non-critical loads. So for most of our customers, they have multiple buses on the platforms, typically a critical and a non-critical bus. The application of a power management system would be to sense what the load is on the platform, and then to close, or rather open up non-essential breakers to bring the load profile back within the capacity of the power generation equipment. So if we were looking at the total plant load, here we're looking again at a year's worth of data. If we look at the 6 engines that are on there, the gray indicates the power capacity of the 6 engines across the temperature profile. So you can see with 6 engines in operation, this customer would never have any deficit, and they would be able to meet the power demands. Up in blue would basically show a 10% increase in that power through the use of Power Boost. Now, if we were to reevaluate this scenario and look at 5 units in operation, with the standard load available on the 5 Taurus 60s, you'd see that for 95% of the use case, we'd be able to meet the power demand requirements. However, there, in red, you'll notice that there's a couple blips here where the 5 units alone would be insufficient to meet the load. That's where we'd be able to execute Power Boost to get the additional capacity, and would be easily able to carry the load with only 5 gas turbines. If you look at it from a spinning reserve capacity, you would see basically the same thing, that anything below the red line would be inaccessible operation, meaning that we have a negative spinning reserve. So again, in gray, you'll see that 5 units of operation sufficient most of the time, but the Power Boost would be required in a few of the edge cases on the left. We also evaluated this with 4 units in operation. You'll see that with 4 units, only about 50% of the time would they be able to make the load, even with the advent of a Power Boost. So in this case here, we'd be looking at least 5 units of operation. So to answer the question about how can we actually, why do customers run the actual power? It's because they need to mitigate against large platform outages. However, based on the historical data, we've shown that we can easily improve the situation and reduce the carbon footprint of the operation on the platform. And so really our solution that we would want to offer is what we call power optimization, which is a combination of using both Power Boost, battery energy storage, and power management systems, either to increase the capacity or to shed non-critical loads. Now, the benefits of this is that you're accumulating engine hours much slowly, so you're basically deferring overhaul costs. So there's a significant financial benefit to running with less machinery. Your fuel costs are obviously less if you have less units in operation, and your emissions profile is significantly less as well. You're running less equipment, and the equipment that you are running, you're running at higher efficiencies. The gas turbine is much more efficient at higher load than low loads. Now, 2 other areas that I'm going to briefly mention is the use of organic Rankine cycle and supercritical CO2 technologies. So with the organic Rankine cycle, essentially what we're doing is we're extracting more useful work out of the exhaust gas of the engine. In this example here, we can basically get an additional 15 to 20% of additional electrical power by supplementing the gas turbine with a supplemental turbine on the back end. We've developed this product specifically for our Mars and Titan product lines, which are our largest gas turbines, specifically for onshore applications. The advantages of this is that it's low capex, we have a standardized design, and it's relatively compact. What this does allow our customers to do is to boost basically the efficiency as well as the power output of a typical installation. And as well, you see here noted that we can save upwards of 12,000 tons of carbon per year. When we look at the direct versus indirect exchange, so with the organic Rankine cycle through direct exchange, we typically would just have the gas turbine, and then from the exhaust we'd have a heat exchanger, and we have a supplemental turbine here extracting additional electrical power, upwards of about 3 megawatts. And again, this is really designed for our Titan and Mars product lines, but the advantage is that it's rather simplistic in its design and doesn't require a whole lot of additional piping. The other area that we're working on is supercritical carbon dioxide technology. So in this, we've partnered with Hanwha Power Systems to come up with a solution that extracts additional power out of the waste heat recovery for a natural gas pipeline scenario. Again, made it up with a Titan 130 gas turbine. And here in my final slide here, just showing you what that particular system looks like. But essentially, we're extracting additional power out of the exhaust gases. And here you see that there's an additional generator that's creating upwards of about 3 megawatts of additional power. And I'll turn it back over to our moderator, Chris Lyons, to introduce our next speaker.